this session is somewhat different from the two previous ones. The two previous ones were focused on the data and on the Mesozoic data. So here we have the chance to have Dick Peltier who will be speaking, and Dick Peltier is really the specialist for the modelization of the ice load on Earth and also the response of the Earth to this ice load. And you know that this affects the momenta of inertia of the Earth, and so it will affect the way the rotation of the Earth, and as well the precession period of the Earth. So it's particularly important in the period where we have ice caps. So that is the first 30 million years, the most recent 30 million years. But it's also important to understand more globally what is the response of the Earth to any load. So, and I met Dick Peltier in Toronto. That was 27 years ago. But so I think Dick has come several times in Paris for, especially mostly at IPGP, but we had not the chance to meet at this time. So I'm very pleased to see you now, and Dick, and I think you can start now and share your screen.
Okay, I'll try. Thank you. So I'll be talking about the 100 kiloyear glacial cycle of the late Cenozoic, but I'm going to focus in this talk on, partially at least, on issues that have to do with the impact of the glacial isostatic adjustment process on Earth rotation. So next slide, Jacques, please. Okay, so just as background, to remind you of the period we're speaking about, first, just a definition of the Cenozoic in terms of deep ocean temperature in red, timescale on the bottom, 65,000 years of Earth history. On the right-hand side, beginning around 30,000 years ago, the oxygen isotope record, which is shown, I think, on the right-hand scale, deep ocean temperature on the left, the meaning of deep sea core oxygen isotope data basically becomes dominated by the ice volume component rather than the temperature component. So we see the Antarctic ice sheet turning on around 35,000 years ago. In the next frame, there's a blow-up of the mid-Pliocene to Pleistocene time scale, beginning at 3.5 million years ago and coming up to the present. And then on the bottom, there's a blow-up of the last roughly 400,000 years of Earth history. And thinking in terms of deep sea core oxygen isotope data, if we look at the surface of the Earth at the last glacial maximum, roughly 21 to 26,000 years ago, the next slide will show the distribution of ice mass on the continents. So next slide, Jacques, have you flipped it on? Okay, so here is the surface of the Ice Age Earth on the left at the last glacial maximum, 21 to 26,000 years ago, and on the right, what I'm showing you is the relative sea level record at the island of Barbados, which is a very good proxy for eustatic sea level, that is for globally average sea level. And you can see that at this time in the past, global sea level was down by about 120 to 125 meters. And this is basically showing the coral record, where the highest quality data are based on the Acropora species of coral. In the top left on the right-hand side, we see a full 100,000 year record, into which this last 21,000 years of record is actually fit in the red in the red curve. So I'll be talking here about the impact of the Ice Age cycle, this 100,000-year Ice Age cycle, on Earth rotation, sea level, and vertical uplift of the continents or depression of the continents. And you can see that this 100,000-year cycle, one cycle of which again is shown in the top left of the plate on the right, has a typical sawtooth type form. It takes about 90,000 years for the system to glaciate and about 10,000 years for the system to deglaciate. So I'm showing you here now what is still, I think, the highest resolution deep sea sedimentary core record of oxygen isotopes that we have. This is the 677 core of Shackleton and al., published in around 1990. And if you look in the leftmost column, this is showing in the top left the period of time in oxygen isotopes from 2 million years ago to 1 million years ago. In the second frame, just below the first in the top left, the time from 1 million years ago to now. And of course, this captures this beautiful transition from a 41 kiloyear world into a 100,000-year world. And in the bottom two frames, I'm showing you the power spectra of the first million years of this record, in which you see the strong dominance of the obliquity cycle at roughly 41,000 years. And in the bottom frame, you can see the enormous burst of power at the 100,000-year cycle, which occurs in roughly the last, I would say, 900,000 years of Earth history. Some people say 8, right? But on the right-hand side, I'm basically showing you the Lascar reconstructions of summertime seasonal insolation at 65 degrees north latitude. Again, the top right is the first million years of this 2 million year record. The second frame is the period from 1 million years ago until now. And in the bottom again, where I'm showing these power spectra of orbital insolation forcing. And you'll notice that we see very clearly in the third from the top on the right-hand side, very strong 41,000 year forcing in the obliquity line. But now in the bottom right-hand frame, what you see is that there is virtually no power at the period of 100,000 years, which on the left of that power spectrum is totally discrepant with the power in the oxygen isotope record. And this is a very strong, and I would argue, the strongest argument we have for the intense nonlinearity of the climate system. Basically, what this says is that the nonlinearity of the climate system enables the system to see the eccentricity modulation of the precession cycle, which if the system were linear, the climate system would not see at all. And this is just to make the point that the main orbital inputs that we're dealing with are those associated with gravitational n-body effects in the solar system. The eccentricity cycle is just sketched on the top, and it has two primary spectral lines, one at 100,000 years and the other roughly at 443,000 years. We then have the obliquity cycle again at 41,000 years, and then the eccentricity modulation of the precessional cycle, basically shown in the bottom right. So what I'm going to go on to discuss now is the way in which this astronomical forcing appears as a pacemaker, if you like, of the process of glaciation and deglaciation, and how the physical system responds in terms of sea level and ice volume. And I want to pay special attention to the impacts of the response of the planet to this orbital forcing At first, in terms of sea level, and I'm going to start by showing you basically the full theory that I've developed in order to describe these effects. So Jacques, if you'll move to the next slide. And having looked at the detailed structure of the theory, I'll then take it apart and then talk in more detail about the orbital forcing components. So this is basically an outline of where I'm going. I've already talked to the first point, that is oxygen isotopes and the late Quaternary or whatever ice age. So next I'm going to talk about the sea level equation and its components. And here we'll have to think immediately about the manner in which variations in Earth rotation feed back onto sea level. And through that physical process, also onto the impact upon the Earth's shape and its evolution associated with the glacial loading and unloading process. So this is the basic structure of the sea level equation. It's the detailed characteristics of the theory that I've developed in order to describe this impact on sea level and ice sheet loading history. This sea level equation is shown in the left-hand plate in its simplest form, in which relative sea level history as a function of longitude, latitude, and time is on the left. And on the right-hand side, that history, space-time history of relative sea level, is given by the product of a function c, again, a function of longitude, latitude, and time, times the difference between the classical geoid, right, which is defined as the gravitational equipotential surface of the sea, minus the variations through time of the local radius of the solid Earth. So this is relative sea level. It's sea level with respect to the continuous deforming shape of the planet, expressed in terms of the variations in local radius as a function of time. And on the next line, this structure is expanded in terms of a detailed representation of this difference between the geoid and local radius. And this expanded form has a mathematical structure, which is a triple convolution integral over two-dimensional space and time of the surface mass load, labeled L in this picture, together with the difference in the green functions, which describe both the geoid and local radius. And I want to make the point here that this structure has a formal name. It's called a Fredholm integral equation of the second kind. And if you're familiar with the famous textbook in mathematical physics by Courant and Hilbert, and you look in the second volume of that set of two volumes, right, you'll discover a very nice section on Fredholm integral equations of both the first and second kinds. What this mathematical structure means is that this integral equation can be solved exactly, right? And I solve it by expanding all of the unknown fields in spherical harmonics, and I unwrap the integral equation to determine the solution S. And you'll notice that this is an integral equation because the unknown field S, relative sea level history, appears not only on the left, but also under the integral sign as well, because the surface load, surface mass per unit area load, L, has two pieces. There is a load associated with the variation of ice thickness as a function of time, which I've called I. And also, the load consists of an ocean component because the system has to conserve mass. Mass, which is added to the continents, is created by evaporation and sequestration of ice on the continents. And of course, that process has to conserve mass. And the thing that makes this integral equation a Fredholm equation of the second kind is because of the term in the third line on the left-hand side, which I've called delta phi of t, divided by g. And that's a term that has to be added to the integral equation in order to make certain that the system conserves mass. So all of the mass that's removed from the ocean to create ice sheets, right, has to be balanced by the mass created, mass produced in the ice sheets. And so when this solution is produced, right, it is by definition a mass conserving solution, right? And furthermore, it's a gravitationally self-consistent solution because by virtue of the manner in which it's constructed, right? The mass conserving nature of the calculation produces a new sea level as a function of time, which is a gravitational equipotential, right? So there's a slowly evolving geoid as a function of time, as the system glaciates and deglaciates, loads and unloads, right? And the kernels in this integral equation, which consist of these two green functions, are shown in the bottom, one for the gravitational potential phi and one for the radial displacement. And these green functions are expressed in terms of spherical harmonic expansions, which have amplitudes, right? Labeled K sub L and H sub L, which are called love numbers. And I'm going to talk a bit about these because you'll want to understand in the innards of this mathematical structure where these critical amplitudes come from. And at the very bottom, you'll see I've written them in terms of normal mode expansions, and I'll talk to you about where these modes come from, which consist of a set of pure exponential decays, right? So this is the bare bones form on the left of the sea level equation. But you'll understand as well that as mass is exchanged between the oceans and the continents, ice on the continents, water in the oceans, right? This will lead to very strong variations in the inertia tensor of the planet. And because it's leading to a very strong variation in the inertia tensor of the planet, there will clearly be strong feedback onto sea level associated with the changing Earth rotation, right? And on the right-hand side, what I'm showing is the variation in this sea level equation that must be introduced in order to capture this influence of rotational feedback onto sea level history. And again, this leads to an extra term, which basically is the convolution of the variation in time of the centrifugal potential associated with the loading and unloading of the continents, again, convolved with a new Green's function, but this Green's function is a Green's function for tidal loading rather than for surface mass loading, as is the case on the left. So this is the full theory on the right-hand side, which includes the influence of rotational feedback. And right away, I want to draw your attention to the very last two lines on this right-hand side form, in which there is first at the top an expression for the expansion of the centrifugal potential. And on the bottom, basically, I'm showing the contributions to that variation in centrifugal potential, which is coming from variations through time of the Cartesian components of the change in the angular velocity of the planet, which are associated with this rotational feedback effect. So let me make a comment next, Jacques, if you'll put on the next slide, about the specific observations of Earth rotation that this theory has been developed to fully explain. And these rotational observations are two in number. The first is shown on the left-hand side in this picture. And it basically shows, as a function of time, the position of the north pole of rotation, right, as a function of time over a period of time of something about 75 years. And this is based on the old ILS data, which consisted of observations of star transits right, made with photozenith tubes beginning in around 1900 up to 1995. And you can see on the inset in this figure in the center, the arrow which represents the direction of secular drift of the North Pole of rotation relative to the surface geography. And you can see that this arrow is pointing towards, roughly towards Hudson Bay, right? So it is this secular drift of the pole, which is called true polar wander, which is one of the things that I've demonstrated this theory to fully explain. But what you'll also see in the X and Y coordinate variations upon which this secular drift exists is what you'll see if you can do the power spectral analysis by eye, okay? What you'll see is a 7-year pulsation of position of the North Pole of rotation in both the X and Y coordinates, right? And that variation is associated with the interference between the 14-month Chandler wobble and the annual wobble of the planet, okay? So it's this secular drift of the pole, which is one of the observational constraints that this theory has been designed to explain. The second of these observational constraints is shown on the right, right? And this consists of the history over roughly 1,500, 2,000, 2,500 years of time, right? Of what we call the non-tidal acceleration of planetary rotation. And this is based on ancient eclipse observations, which are shown basically as the solid data. And if you try to make a prediction of this long series of ancient eclipse observations made by both Babylonian and Chinese astronomers, naked eye astronomers, right? If you try to make a prediction, basically, of the times of occurrence and place of occurrence of these eclipses, right? Based upon the assumption that tidal friction has remained constant as a function of time, right? What you'll discover is that you make a very significant error. And of course, we can measure tidal friction because we have retroreflectors on the moon, which we have used, which we have employed to watch the moon recede from the Earth as a function of time, right? So we have been able to directly measure tidal friction. If we assume that it has been constant and make backdictions, if you like, of the times of occurrence of these total eclipses of the sun and moon, you make an error, right? And the error is such as to imply the action of a non-tidal acceleration of planetary rotation, which works in opposition to the tidal deceleration of planetary rotation. And this non-tidal acceleration of planetary rotation is another of the observational constraints that this theory has been designed to explain. If you go to the next slide, Jacques, I want to next dig into a little of the weeds, if you like, of this theoretical structure and just describe rather quickly, right, the basis on which we determine these love numbers, which are the coefficients in the expansion of the green functions, which appear in this theory, right? So that you'll understand where these fundamental objects actually come from. So we start off with a field theory, which is for, initially the field theory is the same, oops, could we go back one, please, Jacques, sorry. No, I think we're okay. It's just flipped on me. So if you look at this, this slide, oops, at the top, you'll see what are the normal field equations that would be employed, in fact, if on the right-hand side, there were an expression for an inertial acceleration, mass times the second derivative, basically, of displacement, right? This set of this field theory, which is directly coupled, of course, fully coupled to the gravitational field, is exactly the same field theory that we would use to describe the elastic gravitational free oscillations of the planet, which are excited by a typical large amplitude earthquake. So what I've done is to take this field theory and looked at it in the quasi-static limit, in which the inertial force plays no role because the processes of interest are occurring on such a long time scale, right, that the system is evolving in an inertia-free fashion. And there are a number of critical aspects to this coupled set of momentum balance and gravitational equations, which are kind of critical. And I'll just draw your attention to the second term on the left-hand side of the equation for conservation of momentum. This is what's called the term for pre-stress advection. And it's a term with which A.E.H. Love first showed in his famous book entitled Some Problems in Geodynamics, was absolutely critical in the description of processes like the elastic gravitational free oscillations of the planet. It turns out that in the viscoelastic field theory that I've developed to describe the glacial isostasy process, this term for pre-stress advection plays an absolutely critical role in ensuring that the boundary conditions on the surface of the planet are correct also, not only in the elastic limit, but in the viscoelastic limit. So we seek solutions for displacement, which has a radial component U and a tangential component V in the second of these equations, and for the perturbation of the gravitational potential, basically subject to boundary conditions in the bottom left, and this is absolutely not actually appearing well on my screen. This is now better. So we have on the bottom left, we have boundary conditions on the normal tangential components of the stress tensor, and a third boundary condition on the vertical derivative of the gravitational potential. And when we solve this set of equations for U, V, phi, and the stresses, we can express those solutions in terms of these love numbers, which I've mentioned previously play a critical role in the representation for the green functions, which appear in the gravitationally self-consistent theory for relative sea level history. So if you go to the next slide, please, Jacques. So in the top left, what I'm showing you is the constitutive relation, which is employed in this field theory for the viscoelastic structure of the planet, okay? And it relates the time dependence of the stress tensor to the time dependence of the strain tensor, okay? And the trick that I've employed in order to develop the field theory is to write it all in terms of Laplace transforms. So if you rewrite this constitutive relation in the Laplace transform domain, what you'll notice on the first equation on the second set of boxes on the left is that it looks exactly like the constitutive relation for three-dimensional elasticity. And it's a beautiful result that was first demonstrated by Biot in 1954, right? Through a result called the principle of correspondence, right? Which assures us that in linear viscoelastic field theory, right? If we can solve for many times, right? Many values of Laplace transform variable, this effectively elastic problem, right? By varying the time dependence, the Laplace transform dependence of the time-dependent or S-dependent viscoelastic Lemay parameters, Biot assures us that we will have constructed the Laplace transform of the solution, okay? So this is a beautiful trick that works in linear viscoelastic field theory. And it is a trick that enables us to find expansions for these love numbers in terms of a normal mode expansion, right? And for a given input of viscosity structure and elastic structure, and I'm showing you on this slide at the top middle, the old 1066b elastic structure of Freeman Gilbert, right? With a series of viscosity models below it, right? The set of normal modes are shown in the three planes at the bottom for these three different viscosity models, which plot inverse relaxation time for these pure exponential modes of relaxation. For these three different viscosity models, right, for an elastic structure which fits normal mode seismology, right? So there's only one unknown in this problem, aside from the surface loading history, right, which is the depth-dependent viscosity of the object. So you can think of basically the sea level equations, which I've shown you previously, both coupled and uncoupled, right, with rotational feedback or without rotational feedback, as an equation, a Fredholm equation of the second kind, which poses an inverse problem for both the deep viscous structure of the planet and for surface mass loading history, right? If you go to the next slide, Jacques, I'll show you one last result out of the weeds, which is a picture for a set of love numbers for radial displacement as a function of spherical harmonic degree, which basically show as a function of Laplace transform variable S, with the elastic limit at large values of S on the right, lower right, and with the viscous asymptotes shown on the top left, right, for every spherical harmonic degree. And it is the difference at a given spherical harmonic degree between the viscous and elastic asymptotes, which is expanded in terms of the normal modes that I showed you examples of just a moment ago.
Excuse me.
So this is the full structure which I'm employing in order to determine the results, which I'll go on to describe to you now. So Jacques, if you
what is exactly S?
That S is the Laplace transform variable.
Okay.
S is the Laplace transform variable, right? So the limit of large S is the limit of small time, right? And the limit of small s is the limit of long time by the Tauberian theorems, okay? Right? And it's the difference between these asymptotes which carries the amplitude of the viscous response at a given spherical harmonic degree. And that viscous response for every spherical harmonic degree has a different expansion in terms of a set of normal modes of pure exponential relaxation, modes which are found in the Laplace transform plane on the negative real s-axis, and have amplitudes which are determined by the residues at these poles. So this is all a structure which is based on basically classical ideas in functions of a complex variable. So I'm jumping now to actually showing you solutions for the sea level equation, in this case, which includes the influence of rotational feedback. And these solutions are shown here for a series of points, 8 different points. All of them are not actually showing so clearly, which are predictions of the time variation of relative sea level, right? That's the time variation of the separation of the surface of the sea from the surface of the solid Earth. Remember, the sea level equation predicts this time-dependent separation. Of course, this is exactly what we observe in nature, okay? So in the top left, I'm showing you results for a data set that comes from Hudson Bay, and a point in southeast Hudson Bay, which, as I'll go on to show you, was one of the main centers of post-glacial rebound of the crust, right? That developed at the end of the last of these 100,000 year cycles, subsequent to which the land has been continuously rising out of the sea, right? At present, the rate of that rise out of the sea in this region is about 1.5 centimeters every year. And you'll see that this theory fits the data in this region with high accuracy. The data are actually determined by radiocarbon dating, right, of sea level indicators, typically shells, pardon me, right, which cover basically a portion of the Holocene period of Earth history, which is the last 10,000 years. And what I'm showing you on this figure is a number of results from different locations, both North America and elsewhere, of these sea level histories and comparisons of these sea level histories with actual radiocarbon dated sea level observations, right? And you can see that in spite of the fact that the sea level histories have a wide range of different structures in terms of their time dependence, the theory is picking up these structures beautifully.
What is it's the time in a millennium of years on the axis?
This is the time in thousands of years before present. Present day is in the, if you look at the top left-hand time series, the present day is in the lower right-hand corner of the box in the top left comparison, right? So that point is always a point of observation, and variations in relative sea level are measured with respect to the measurements that are made at the modern day. So the theory is designed to match sea level at every location at the present day, right? And it makes a prediction of the history of the separation between sea level and the surface of the solid Earth. And in this top left frame, what this is showing is that the solid Earth has been rebounding out of the sea, right, as a function of time, which is occurring at a decreasing rate as time goes forward, right? If you look in the center of this picture, what I've done here is to superimpose upon the locations of the 8 locations for which relative sea level is shown. I'm showing you a picture of the present day predicted time rate of change, right, of relative sea level history that is predicted by the theory at every point on the Earth's surface. And we can do this even over the continents, right? Because we are able to make a prediction of where sea level would be, right? We're able to do an analytical continuation of the surface of constant potential, which determines the level of the sea right through the continents. So we're able to make a picture of this time-dependent separation of the surface of the sea and the surface of the solid Earth everywhere. And here I just want to draw your attention to the fact that if you look by eye at this picture, you'll notice that it looks like a degree 2 and order 1 spherical harmonic overprint on this picture, right? In the top right, you see red. In the bottom left, you see red. In the bottom right, you see blue primarily. In the top left, you see blue. And you'll understand very shortly the reason for this degree 2 and order 1 overprint. But what you'll also see is in purple, regions of strong post-glacial rebound of the crust over northern part of North America, over Greenland, over northwestern Europe, over the region which was once covered by the Barents Sea ice sheet, over the region that was once covered by the Fennoscandian ice sheet. And you'll see in Antarctica, there's rebound occurring right, as a consequence of ice loss. And you'll see in the southern tip of South America, rebound of the crust predicted as a consequence of the loss of what we call the Patagonian ice sheet, which existed on the surface in this region at the last maximum of glaciation. So I want now to begin to take apart this generally successful picture of the ability of the theory to explain relative sea level histories, right? And in doing so, I want to draw your attention to several very interesting things. But before we switch to the next slide, I want to just briefly comment as to the origins of what looks like a degree 2 and order 1 overprint on top of this picture of the present day prediction of vertical variations of relative sea level. I showed you in the form of the sea level equation, which includes rotational feedback, I drew your attention to the fact that there were degree 2 and order 1 components in the representation of the centrifugal potential, right, through which this rotational feedback occurs. And that degree 2 and order 1, those degree 2 and order 1 components, right, actually exist because of the true polar wander of the North Pole of rotation, right, that has been occurring, as I showed you in the ILS data, very clearly as a function of time through the secular drift of the pole towards Hudson Bay, right? And it is the degree 2 and order 1 contribution to the centrifugal potential, right, that captures this influence of rotational feedback, is entirely associated with this secular drift of the pole towards Hudson Bay. So if we go to the next slide, please, Jacques. So this makes this even clearer, okay? And what I'm doing here is for a particular choice of viscosity model, I'm showing you the present day time dependence of geoid height, right? And remember, the geoid, I oftentimes also call absolute sea level. It's the level of the sea measured with respect to the center of mass of the planet, okay? Right? We can decompose that time dependence of geoid height into two pieces. The first piece we can represent as the time dependence of relative sea level history measured with respect to the surface of the solid Earth, right? If we add to that the time rate of change of the local radius of the solid Earth itself, right, we then get sea level with respect to the center of mass of the planet, okay? And so this geoid, this classical geoid of formal geodesy, right, turns out to be an extremely critical structure in terms of this viscoelastic field theory of planetary evolution in response to ice sheet loading and unloading. So if you look at the graphics in the center of this slide, at the top, basically I'm showing you the time-dependent variation of relative sea level, okay? In the center, I'm showing you, in fact, the negative of the time rate of change of local radius. And you'll notice that these two pieces, right, because of the minus sign in front of the time rate of change of local radius, right, are very well correlated, almost perfectly correlated, okay? But if we now add the time rate of change of relative sea level on the top to the time rate of change of local radius, okay, to get the actual geoid, right? Note the positive sign before DRAD. We get the picture at the bottom, which shows this perfect degree 2 and order 1 structure, okay? The geoid is totally dominated, right, by the influence upon relative sea level history, right, of the slow migration of the North Pole of rotation towards Hudson Bay, right? Because it is that degree 2 and order 1 structure which carries the influence on the centrifugal potential, right, of the process associated with the feedback of rotation onto sea level history. So this is a beautiful, very beautiful result, which I first produced in response to a request by NASA before the GRACE satellites were launched. And if you look in the brochure that was produced at the time the GRACE satellites were launched, you'll see a picture from my group, which is showing this degree 2 and order 1 structure, which turned out to be exactly as observed by the GRACE satellites. So this is a direct demonstration of the importance of this rotational feedback effect on relative sea level history, an effect which is made most apparent in terms of the time dependence of present day geoid height, which is exactly the field that the GRACE satellites have been designed to measure. So I'm going to go a little bit further now in the next slide, Jacques, in talking about detailed sort of observations. First thing I want to say, though, is that it turns out that GRACE is actually blind to a component of the variation in centrifugal potential, right? Blind because of the fact that the satellites constitute an inertial observer, right? And this is absolutely critical to understanding what GRACE sees. GRACE is totally blind to a component of the degree 2 and order 1 spherical harmonic variations in the geoid. That component, which is due to instantaneous changes in the Earth's state of rotation, because it can't distinguish between these, right, and gravitation itself, okay? Right? So if you decompose, and I've generated basically two versions of this theory, one which describes the geoid that GRACE is able to see in the top right, pardon me, and the geoid which actually exists when the geoid is defined as the gravitational potential which overlaps the surface of the sea in the absence of currents and tides, right? There's a significant difference in these two degree 2 components. So when you're computing sea level history, you have to use the love numbers which are associated with the real geoid, right? And all of the impact on the geoid that's associated with rotation, right? However, if you want to look at the time dependence of the geoid to compare it with that which GRACE can observe, then you'll notice that the GRACE observable geoid, which still has this strong degree 2 and order 1 structure, differs significantly, right, from the degree 2 and order 1 structure of the true geoid when this is defined in terms of the gravitational potential of the sea, which defines the surface of the sea in the absence of currents and tides. So this is an absolutely critical idea in the interpretation of GRACE data, which I'll eventually go on to do. One of the, just to make one more comment basically on how critical this geoid is, okay, when it's properly defined, right? And when it is computed for a history of loading of the continents, which actually fits the observations, right? And here I'm basically showing these two components of the geoid over North America. In the top frame in the left-hand side, I'm showing you the rate of vertical displacement of the crust, right? The time rate of change of rebound of the crust of the solid Earth. in the center of the frame, I'm showing you the time rate of change of sea level fall. And you can see that they are exactly out of phase, okay? As in the global fields I showed you previously. But now you can see that in fact, the loading history of this continent was characterized by a triple dome structure. There were maxima of ice thickness in 3 different regions, one in the southeast of Hudson Bay, one to the west, northwest of Hudson Bay, right? And one in the elbow of Baffin Island, which is in the region called Fox Basin, okay? And you can see that in the theory which fits the data, and I'm going to go on to show you the nature of these fits momentarily. I've already shown you some sea level fits, right? But when you add these 2 fields together, you get a time rate of change of geoid height, right? Which is much smaller than either of the other of these 2 component fields, right? And which has a magnitude which is basically on the order of a millimeter per year. And it's very important to understand that in order to make a geoid prediction, right, a formal geoid prediction, time rate of change of geoid height prediction, you need to have a global model. It must be a fully global model. It cannot consist of a number of different models, right, for the removal of ice from different regions, right, because these are coupled together through a single geoid, okay? And this comes very clear when you realize that just from the time dependence of geoid height alone, one is able, from a full global model, right, one is able to make a prediction of every point on the surface, right, of what should be the vertical rate of rebound or depression of the crust, right? So the University of Toronto model of this process is absolutely unique, right, internationally, in that it is the only model which is fully global in character, right? And which has been designed to optimally fit all of the data that are available, including those from GPS satellites and the gray satellites, as I'll go on to show you. Please, next one, Jacques. And I'm going to show you basically results for vertical motion of the crust over North America from these literally hundreds and hundreds of GPS receivers that have been placed either in permanent mode or in campaign mode over the surface of the North American continent. And in showing you comparisons between what the GPS satellite sees and what the global model of glacial isostatic adjustment predicts. So I'm going to now show you main results from 2 space geodetic observation platforms that have been used to confirm this model. The first are the gray satellites shown on the left. The second is the constellation of GPS satellites shown basically on the right. Next slide, please. So I'm going to first look at what the GPS constellation sees in terms of vertical motion of the crust, right, over the North American sector. I'm going to be showing you comparisons between 2 different loading histories for the North American continent. One called, the most recent one called Ice6G, and the previous one, which is called Ice5G. And there's a huge difference, as you'll see, by comparing the frames in the top left and in the center at the top, between the thickness of the ice that was assumed to exist over the North American continent, particularly in the region west of Hudson Bay. So in the 5G model, it turned out from the GPS analyses previously performed, we were able to identify an ice thickness error that was somewhere between 500 meters and a kilometer, a huge error, right? And so I'm going to show you results comparing the 6G and 5G models next. And I'm going to be showing you comparisons along a set of trajectories traverses across North America, basically comparing 6G predictions of the model shown in blue, and two versions of the 5G model. One, my own, which was published in 2004, and the second, a reconstruction of the 5G predictions produced by one of the students in John Var's group at the time, who used a completely different methodology to make the prediction. And comparing dashed red and dashed green, right, you can see that these two models of ICE 5G are almost identical, and both grossly misfit the observations on this first traverse, AA prime. And this is found to be the case when you go over all traverses, and we've got about 16 of them across North America, right? We have excellent fits to the observations, right, from the I6G model. And misfits sometimes are very large, sometimes less large, right? Depending upon how close the receivers are to this region where there was a very significant adjustment in ice thickness. Next slide, Jacques. And I can go through this now very, very quickly. Same is true on this set of traverses, right? The old models grossly misfit the observations in many places. Next slide, Jacques, right? What you can also see is this model is capturing the regions of subsidence, which lay outside the regions that in which the continent was actually loaded by ice. So the land is going up where it was once ice covered, and it's going down where it wasn't ice covered, right? And what I'm showing you here is a check on the quality of this model now using GRACE. The data I was showing you previously were from GPS receivers measuring vertical motion of the crust. Now I'm showing you the GRACE observations. Here is GRACE in the top left, right? From one of the latest releases prior to the launch of the GRACE follow-on mission. And here you can see the Toronto predictions of what GRACE should be observing, right? And they're effectively identical, so much so that all of the major centers which are responsible for GRACE analysis are now using the Toronto predictions in order to remove the influence of the Ice Age cycle, right? So as to reveal more clearly the processes associated with global warming, modern global warming. And you can see in the top left the difference between Toronto predictions, GRACE observations, and you can see there's a large misfit over regions which were feeling very large ice loss, have been feeling very large ice loss, like Greenland and Alaska, right? And you can see the very large errors that were made to the fit explanation of GRACE data by the previous ICE 5G model, right? So we're in a position now, because we have demonstrated that GPS models that fit GPS observations are also able to beautifully fit observations of the GRACE satellite. So if you go next, I'll wind this up very quickly now, Jacques, in the next two. So if you look in Antarctica, we can do the same thing. Remember, this is a global model. Next slide, please. So the model includes not only a loading and unloading history for North America, for Northwestern Europe, for Greenland, back one, please, but also for Antarctica. Back another one. The more complicated the slide, the slower it runs. So this is now basically showing the Center for Space Research GRACE results in the top left, the I6G prediction in the center, in which for Antarctica, I6G is predicting very large rates of ice loss due to the last glacial cycle in both the Weddell Sea and the Ross Sea embayments of Antarctica, right? And using the CSR data, again, if you subtract 6G from GRACE in the top, in the right-hand side in the top row, what you'll see revealed are the regions of very large ice mass loss which are now occurring associated with the global warming process over both the Amundsen Sea sector of Antarctica and the Antarctic Peninsula, and over this range of time, increases in mass in the region to the east of the Weddell Sea, which is associated with increased, basically, snow load. So I'll end, if you go to the next slide, just with one final comment on the current state of play. We're now very deeply involved in taking this model, which so well fits such a wide range of data, and inserting it into a modern climate model, right, as boundary conditions, right, for the coupled atmosphere-ocean climate system. And if you go to the next slide, this is enabling us to explain an observation that was first made over 25 years ago by Willie Dansgaard and others, based on deep ice cores which were drilled in the Greenland ice sheet. This revealed the existence in the top frame, you can see it with the blow up in the bottom, of very intense millennium timescale oscillations in climate over Greenland. And if you go to the next slide, Jacques, what we've been able to do is to explain these oscillations in terms of time dependence of the deep thermohaline circulation of the oceans, right? Simply by taking the boundary conditions that have been inferred on the basis of the glacial isostatic adjustment analysis and inserting them into a fully modern CMIP5 level 1 degree by 1 degree climate model. And if you show the next slide, Jacques, this has really enabled us to explain, really fully explain, this so-called Dansgaard-Oshker oscillation of glacial climate, basically as a direct response to what we call a Heinrich event hit to the global ocean associated with freshwater forcing of the North Atlantic, right? Which is shown here to deliver an almost perfect relaxation oscillation, right? In response to this striking of the surface, right, by strong freshwater forcing. We're able to get, for the first time, demonstrate that a modern, fully coupled atmosphere, ocean, sea ice climate model is able to immediately explain this famous oscillation that was first revealed by Willie Dansgaard and others looking at the GRIP ice cores. As it says, this is the end, and I'm very sorry, and I apologize profusely for having such a problem getting started with this. I feel very badly about this.
Thanks a lot, Dick, for this talk that is very, also it's a complicated subject. I found that you explain it quite clearly. Of course, many people in the audience don't have all the background, but I think to get all of it, but they will understand the general stuff. So
yeah, hopefully I've communicated something of the flavor.
Yes, no, sure, certainly you have done more than that. So now we can open for the question, and you can raise the hand, the little hand, which should be somewhere. I don't know where they are. So if you want if there are some questions, I have one immediately on this last slide.
Yes.
So the red curve here is your model. I don't understand exactly.
No, okay, let me add a little bit. You can't really see
which are the data, which are the models, the result of the model. I don't understand.
First of all, this is all model, right?
All model.
The blue curve, right, is the variation, predicted variation of as a function of time, right, of the strength of the overturning circulation in sphere groups. Okay. The red curve, okay, is the top of the atmosphere variation, right, of the difference between shortwave incoming insolation and long wave outgoing insolation. Okay. And the dashed line through the center of this, right, is actually the point in which there is a perfect match between incoming shortwave insolation from the sun and outgoing longwave insolation to space, okay? And you can see that this almost perfect relaxation oscillation is around this state of perfect balance, perfect energy balance of the planet. If this were not the case, this would not be a viable solution, right, to the problem, right? This is an almost perfect limit cycle, as we say in the language of nonlinear dynamics, right, that has been captured by this extremely complicated modern coupled atmosphere ocean sea ice dynamical structure.
Okay. Any other questions?
So on the hot side, on the strong side of the relaxation oscillation, when the blue curve is at a peak, you can see that the red curve is also at a peak, right? So when the overturning circulation is strong, right, the system is in a hot state, and the emission of long wave radiation to space is higher than the incoming shortwave radiation, and vice versa.
Okay. And this correspond to this 700 years correspond to the observed rapid cycle?
I'm showing you here, the picture I'm showing you here is from the first paper we published on this. The actual period of the dominant relaxation oscillation is closer to 1,000 years. If you were to look at the most recent paper from that I have published in JGR Oceans, which came out last year, right? You would see in that paper that we have been able to understand in much greater mathematical detail what the constraints are on the actual period of the oscillation, which is a bit longer, right, than the structures which are shown here, right? The actual observed periods are anywhere between 2, even 3,000 years and 1,000 years, right? So in the recently published paper in JGR Oceans, those who are interested would find a very detailed discussion on what controls exactly that period.
Okay. Is there any question from the audience?
Yes, I have a question.
Yes.
So how hard will it be to leverage all of this model into understanding the change in the Earth's dynamical ellipticity going back in time, in case we want to go to the cyclostratigraphic record and try to model that better? You know, the dynamical ellipticity, the change in the precession rate of the Earth. What do you think the maximum and minimum changes in K will be, you know, across these glacial cycles?
Some years ago, we published a paper on the forced changes in precession. That's quite a long time ago. I think it was around the time, in fact, that Jacques visited us.
That's right. So how would you change it now?
You mean how is it changing?
How does this update? How does this work? Clearly updates all of those results.
What we found in this early work is that these predicted changes were actually quite small, but my expectation is that as you go further and further back in time, they would become, in principle, more and more important.
Okay, so, all right.
What is, you show that the model 6 is a significant difference with respect to the model 5.
Yes.
How confident are you now with the model, with the ICE6 model? Will you tell us in a few years that the model 7 has big difference with the model 6, or do you
we've already published a Model 7. And there's small changes, right? In Model 7, which was published in the doctoral thesis of Kevin Roy at the University of Toronto, right? We have shown by ingesting further observations of relative sea level history, in that case from along the east coast of the United States, along the southernmost part of the east coast of the United States, where Model 6 was making significant misfits in the prediction of the relative sea level record. What we've demonstrated in these papers is that the viscosity model, which is one of the critical components of Model 6, was insufficiently stiff in the deepest mantle, right? Mm-hmm. And this was a discovery which was actually very happy to find, because our expectation is that in terms of the depth dependence of viscosity in the mantle of the Earth, that this viscosity should rise significantly as a function of the difference in slope of the mantle melting curve, right? And the mantle adiabat. Because the mantle is mixed convectively, we expect that its core would be adiabatic, okay? But the melting curve rises very steeply as a function of increasing pressure in the solid, right? And so based on this, what we call homologous temperature argument, right? It is expected that the viscosity of the deep Earth should continue to rise monotonically below the 660 kilometer seismic transition, right? And in the 7G model, what we discovered is that, in fact, there were data of high quality that demanded that this variation, increasing variation of viscosity with depth, had to be introduced, right? So it makes predictions which are in certain regions, like relative sea level data along the southernmost part of the US East Coast, which enable us to fit observations that weren't ingested in the previous inversions, right? So this is a continuing process. As new data become available, they're tested against the predictions of the current model, and where necessary, the model is updated. And that's one of the examples, right, of the most recent updates, which are described in a pair of papers with Kevin and I that appeared in Geophysical Journal International about 2 years ago now, 2.5 years ago now.
Okay, thanks. Any other questions from the audience? Because if not, I have one still. I understand well what are the new data for the present time, which are given by GPS data and which are given also by satellite, like the GRACE satellite. This gives very accurate data. But what are the critical data that we can gain in the past for the reconstruction, for the past reconstruction, to constrain this ice load evolution?
One of the most interesting pieces of data, and there has been interesting debate between my group and others on this, are data that constrain the loading history in regions which are well removed from coastlines, right? So the main data that we ingest into the theory, right, which is predicting relative sea level history, are obviously data that come from coastlines. But for example, in North America and in Greenland, right, significant variations in loading history have occurred in regions, for example, in Western Canada, east of the Rocky Mountains, north of the US-Canada border, in which the sea is well removed from the location where it is imagined that very significant ice loss has occurred. So there are new data sets which have been discussed by the ANU group and by my own group in Toronto, for example, that have to do with observations that are made on what are called proglacial strand lines in lakes that ringed the ice sheet during its collapse phase, right? So there are new data like this, which are being brought to bear to try to better constrain the loading history in regions which are well removed from coastlines.
So
That's a critical aspect of this.
So what kind of data precisely it is? It's
well, as the Laurentide ice sheet, as we call it, began to decay, right, surrounding the western and southern edge of the ice sheet as it was melting back, right, because the surface around the edge of the ice sheet had been depressed by the load, right, it leaves a trench around the edge of the ice sheet, which is filled by meltwater as the ice sheet retreats, right? This is the origin of all of the lakes, right, that ring the present day Canadian Shield, Great Bear Lake, Great Slave Lake, right? The Great Lakes, all of these lakes were filled, right, by meltwater that was released to the surface of the continent, right, during the deglaciation of North America, right? So we're now using detailed observations, right, that we can make in association with these lakes, right, to further constrain the model because they were emplaced in regions that were well removed from the coastline. So this turns out to be a very interesting source of new information, which has to be confronted with the theory and which is proving to be very useful.
Okay, that's very nice. So are there any, Gwenaël, do you have any hint that are given by the, or Mohammad? Mohammad is looking to the sea level equation, so he should be able,
yes.
He should have some feedback on this.
And I had a couple of questions, but basically you all asked of them, specifically on the update of the I7G model. If I can ask another question, which is one of the points that you brought at the very beginning of the presentation. A very basic question is how do you decide, for example, you mentioned that the Barbados data is an indicator of your static sea level variation. So it's like a far field indicator, right?
Yes.
So
yes.
How do you decide on certain geographical positions being far field or near field? And I'm guessing it's similar for both the sea level data and maybe also oxygen isotopes or something.
Yeah, I mean the critical nature of the Barbados data set is basically because it's sufficiently far away from the main centers of glacial loading and unloading, and offshore, right, of the South American continent, north of the continental margin, right, that when you do direct comparisons of what I call ice equivalent sea level history, that is, if you make a comparison between the theoretical prediction that you would expect for relative sea level history at Barbados, simply by doing the following thing. Assume, right, that the surface area of the oceans, for example, haven't changed. Okay, of course they do during the loading and unloading process, but assume, right, that they haven't changed. Then compute the total mass added to the oceans as a function of time, right, by ice loss from the continents, right, to make a prediction of what ice equivalent sea level history should be at Barbados.
Okay.
And the beautiful thing is that when you think in terms of ice equivalent sea level history, right, then it fits the Barbados observations beautifully. And the theory, of course, which includes all of the redistribution of water among the ocean basins, right, also fits the Barbados data perfectly. Okay. So this demonstrates that the Barbados data point, right, is very important, not only because it's the longest record of sea level history we have, right? But that it is recording a very close facsimile to ice equivalent sea level history, which is to say the amount of mass that was added to the global ocean basins by the disintegration of all continental ice sheets across the glacial interglacial transition. This is an astonishing thing, right? And one of my former students and his student has looked in detail around the Earth using the same theory to find other places where there are similar fits or similar expectations, pardon me.
Yeah.
And there are a few, right? But these sites turn out to be places where there are no data. Okay. Right. So this is what really makes the Barbados record so fantastic. That is that the record goes right back to of order 32,000 years before present.
Okay.
Of course, the quality of the coral record degrades prior to around 21,000 years ago, because you run out of Acropora palmata species that live in the present ecology within 5 meters of sea level, right? So, you know, there are arguments that I've made in the 2015 paper where I looked in great detail at the Barbados record, right, as to why you should choose the total depression of sea level, which I choose in the ICE6G model, which is somewhere around 125 meters, right, as a best fit to the total depression of sea level, which occurred across the transition. So this is the Barbados record is a very special place. There have been long records, but not of equivalent quality, which have been obtained from a number of sites. Edward Bard has worked on one of these. The group that has worked in Indonesia and Southeast Asia has another record, which to different degrees either see or don't see, right, the main meltwater pulses, which have been a target for all of us who've been trying to understand the glacial interglacial transition. So I would say that this is all clearly a work in progress. When new data becomes available, we try to absorb it, integrate it into the picture. And the goal, of course, is to try to find things which totally rule out, which finally say, sorry, there's a fundamental error in what you are doing, right? We want to break the model in order that we can learn more.
Yeah.
So if you're working on this, I hope you're trying to break the model, because that's the only way where we'll really learn new things, I think.
Thank you.
Okay. Do you have other questions, Mohammed? It's a time to ask them, you see.
Yeah. Basically, it was a very nice presentation, a kind of historical one on the whole topic, which I've been trying to understand for the past year. I have another basic question, which is,
Yes.
I mean, your models, NG, whatever model. So I've seen the data that you provide on your website, and they
Yes.
all go back. I guess the 7G, for example, or the 6G goes back to around 200,000 years ago, right?
I need to be, this is a good point in the discussion to be careful. All of the analyses of sea level history that I present are based upon the assumption of a single 100,000 year glacial cycle.
Okay.
And my understanding is that this group is interested in even much longer timescales. The only data which are actually quite dependent on more than a single glacial cycle are the data that have to do with Earth rotation, right? The predictions of the secular drift of the North Pole of rotation, the prediction of the non-tidal acceleration of planetary rotation. In order to get stable results for these predictions, I will typically use at least 2, sometimes even more 100,000 year cycles. And when you go further and further, deeper and deeper into the past history of the variation of this 100,000 year cycle, your ability to, with precision, know precisely what the mass was that was removed from every region, right, diminishes as you go further and further back in time, right?
Yeah, but what's the major constraint, or why is it diminishing basically? Why are we losing information with time? Why do you have a limit on your ice model?
Yeah, I mean, okay, let me try to put it this way, okay? The oxygen isotope observations in deep sea sedimentary cores provides you a direct estimate of mass, right? But you don't know where that mass was.
Exactly.
For the last glacial cycle, you see, we have what we call terminal moraines on the continents, both in Northwestern Europe, in North America, unfortunately not Greenland and not so much in Antarctica, but for the two main centers of glaciation, we have what we call deglaciation isochrones, right? We know from last glacial maximum up to the present, we know where the edge of the ice sheet was, right? But we don't know because there's no evidence, right? Or very little evidence, let me not say no, there's very little evidence of where the edge of the ice sheet was prior to last glacial maximum, basically because every time the ice sheet advances, it erases the blackboard of evidence, right? So the issue becomes, okay, we can make, this is what I do, I make an approximation going back to earlier glacial cycles, right? By simply assuming that the edges were always in the same place, and then partitioning the mass between the regions that were glaciated, right? According to the areas that they were, by which that were covered by this mass.
Yeah.
Right?
Yeah.
And it's very difficult to do better than that, I believe. But what we don't see over the past many hundreds of thousands of years are strong evidence, except for example, over the Russian plain, which is a place that during the last glacial cycle wasn't significantly covered, but which was significantly covered, we know, during earlier glacial cycles, right? So there are certain regions, right, where we know if we assume that the area coverage was the same, that where we would be making large errors, okay? And that's one region in Northwestern Europe over the Russian plain where we know then in earlier glacial cycles, there were significant mass. We can see a little bit as well over North America in the region south of the US-Canada border where in earlier glacial events, the ice sheet extended somewhat further south, right? Yeah. But we don't know because there's no evidence, can't be any evidence of times in the past where the edges of the ice sheet, right, were significantly within the margins that were characteristic of the last glacial maximum. Again, because every glacial advance that occurred thereafter erased the blackboard.
Yeah.
So it's, I mean, this is an extremely complicated inverse problem, right? For both mantle viscosity and for ice cover and errors. There are correlated errors between these two characteristics of the model. And we have to proceed using data-centric analyses, right? Which enable us to judiciously work with the observations in such a way as to avoid as much as possible impact of the correlation of these errors.
Okay, thanks for this very clear explanation. So yes, Matthias?
Just related to your last point, I just had a question. You say a very large error. Can I just ask how large that is? Is that different orders of magnitude? Because, and I'm also asking because some of us are deep time geologists, let's say millions, even hundreds of millions of years ago.
Yes, yes, yes.
Sorry?
I'm just waiting for the rest of your comments.
And I was just wondering, is there any point in, because sometimes we run climate models or coupled climate ice sheet models to try to reconstruct glacial history, let's say 300 million years ago, with huge uncertainties, of course, but that's why I was wondering, what's the order of magnitude if you're saying large errors? And is there,
well, in terms of the glacial cycle previous to the last one, right, where young Inge Svensson and Jan Mangerud, for example, have continued to do this beautiful work. Mangerud is just recently retired, I believe, but their work over the Russian plain is absolutely critical, to our understanding of the glacial history of Northwestern Europe. But even though they are able to tell us that in previous glacial cycles, the ice margin, right, was far to the south and east of where it was at maximum during the last 100,000 year cycle, we don't know how thick the ice was, right? Right, so we have a lack of a mass constraint.
But we have the global evaluation of the ice with the delta 18.
No. I mean, delta 18 gives you an excellent picture going back. Well,
but it's a global number. It's one number for all the years.
Pardon?
It's a global number. It's a number.
Exactly.
There is no local.
There's no local information. Exactly. Right. So basically, it's a first order. What you're able to do is to say, well, the ice cover would be focused near the poles, right? Right, and so we can use the ideas that have been developed on glacial inception by many of the groups, including mine, that have worked on that problem, right? Why it is, for example, over North America, that the ice sheet nucleates over Ellesmere Island and northern Baffin Island, right? We can, our ability to actually reconstruct the glacial onset problem is much better now than it has ever been. Yeah. Right, so the ice will appear right in highest and high northern latitudes and southern latitudes first, right? But it is a global measure, and it's deconvolving that global measure and giving it local meaning, which is at the heart of trying to understand issues like rotational feedback, right? Because the impact on the planet's rotational state really depends very strongly, right, on the distribution of time-dependent mass relative to the poles. And this beautiful result we have, right, on the explanation of the polar wander component of Earth's rotational state during the last deglaciation, right? I mean, that strong polar wander impact basically comes because the North American ice sheet was sufficiently removed from the North Pole, right? That polar wander is dramatically more important in terms of rotational feedback than is the effect of the variation in the length of day. Even though the latter, of course, is extremely interesting physically.
Okay.
So could we use polar wander reconstructions for our type of problems?
Yes.
That could be a type of data that's available.
No, absolutely. Yeah. I mean, and the quality of these reconstructions, of course, brings into play more physics than than just time-dependent ice load, right?
Okay.
Right. So if you go back hundreds of millions of years in time, you're looking at, plate tectonic effects, redistribution of the continents, and all of that, of course, is very, very interesting, right? So as you reach further and further back in time, you have to become much more cognizant of the full range of geophysical physical impacts that come into play.
Okay. Are there any other questions from the audience? Doesn't mean that we could not continue some very technical discussion on the side some time further, but maybe we will stop here for this time and thank again Dick Peltier for his very clear talk. I think very comprehensive, and that gives it gives really a much clearer view, at least for me. I must say that of all the implications that are here.
Thank you
Thank
so
you
much.
very much. Thank you very much, Jacques. And let me end again by apologizing to you all profusely for subjecting you to this chaotic beginning.
And
It just made it better. It made it better. So thank you so much. I have to go, but it was a wonderful talk.
The next talk will be, so within 1 month, we have not fixed the date yet. And it will be somewhat in the continuation because it will be by Giorgio Spada.
Ah, yes.
The computation of the love number and so it's really also the answer of the also of the ice load and the response of the Earth, and but in a different view.
Yes, 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 yes. No, that's good. You need different perspectives.
Yes, that's. Okay.
Okay, again, thank you very much, everyone, for listening.